Yeah, Blake,
Hey, good afternoon.
good afternoon. It was nice of you to
Hey,
redeliver to me my PowerPoint.
yeah, I sent you a PowerPoint instead of, oh man, I'm so sorry.
No, don't worry about it. I got it now. I haven't looked at it yet. I'll look to
Okay.
see that I can read the attachment. If I can't read the attachment, you'll get an email from me immediately. Okay.
Okay, great. Yeah, let me know if I got to alter it anyway. I did provide some proof there. The document
No,
hasn't been
no,
altered
no.
since the
Don't
5th,
worry about
so
it. Don't
okay.
worry about it.
Okay.
I
I
mean,
forgot a quiz yesterday too. I checked. I didn't think anything was due yesterday, so that's on me, but at least two of them were dropped, so we're good.
okay, good enough.
Yeah.
You didn't have any trouble getting in here, right? Because you seem to be the only one here so far.
Yeah, no, sir. It was
All right,
easy. Yep.
good enough. Might be I had three people in my morning class, so more people
Thanks.
can dropping out. Have you been in touch with anybody else?
I don't know anyone at SPC, so.
I'm at a loss. I really am at a loss because I don't know how these people are getting through these tests. I
Yeah.
It's a humbling thing, Blake. It makes me seem like I'm not even worth. It's not even worth having me here. But hey, if they can get it in some other way, I just would like to know what they're doing so that I can duplicate it in the future. That's all.
Yeah. Oh,
Hi,
they
Joe.
helped me a lot, so.
Oh, good, Blake. Joe, how you doing? You in here, Joe?
Oh, I have all tabbed. Yeah, what's up?
No, no problem. I just wanted to know you were in here. Uh, Now it's 5:30 now, so I'm going to go ahead and start the beginning because the first little bit of this is a review anyway. Okay. Now, sorry. All right, you seeing the slideshow, guys?
Yeah.
Okay. Bottom line, when we're doing Lewis dot structures, we are going to write the molecular formula down. We're going to write the elements down on a piece of paper. Generally speaking, we're going to put the least electronegative element in the center. When I go through formal charges later today, I'm going to explain why that is. Next thing, I'm going to add up all the valence electrons. If there's an ion, I need to account for that ion. If I have PO4 3 minus, I have to add 3 to the number of valence electrons from the four oxygens and the 1 phosphorus. So phosphorus gives me 5. The 4 oxygens give me 4 each. I have to add another 3 electrons. That makes 32. Going through the rules subsequent to that. Once the elements are done on a piece of paper, I have to draw a line between each of the elements. This indicates the bond. I subtract the number of electrons I use. If I draw a line, that's 2 electrons. Next, I'm going to fill the terminal atoms with pairs of electrons. And you have to note that hydrogen, because it only needs 2, will not take any more electrons if it's bonded to something. I subtract the electrons I put around the terminal atoms from the remaining electrons. Anything left over goes on the center atom. If the center atom doesn't have 8, what you do is you take 2 off of the terminal atom, put those 2 between the center atom and that terminal atom. You're making a double bond. You're filling out the 8 around the center atom. Last thing, check everything. Okay? Seem pretty reasonable?
Yeah.
Dylan, you're here, right, Dylan? You popped up.
Yes.
Okay. Now I'm going to do something a little bit differently today. It seemed to work out good in the first lab, and that is it's easier for me to do this crap if I'm doing it on a board. Okay? So if I'm dealing with this, I have selenium dioxide. The selenium is going to give me how many electrons? How many valence?
6.
6.
Thank you. Each oxygen is going to give me.
6.
6.
So I have a total of how many? By the way, this
18.
Etch-a-Sketch thing doesn't work all that great. How many?
16. 18.
Okay, we'll go with your second guess.
Yeah, that's what I meant to say.
All right, now I'm going to put these on a piece of paper with the least electronegative in the center. Undo. Undo. This Etch-a-Sketch stuff just does not work well for me. All right, I'm going to put one pair of electrons between those. This gives me how many left?
14.
14. 1, 2, 3, 4, 5, 6. Those are lone pairs, so that's minus another 12. I have 2 left. Where do those 2 electrons go?
The central atom.
All right. Now, does the center atom have 8 electrons?
No.
So I got to take one set of lone pairs from the terminal and I got to put it in the center and I got to erase this one. Is this making sense, guys?
Yes.
All right. Now, we're going to go to something that doesn't make sense. This molecule exists. It does exist in the world. Okay. How many valence electrons does beryllium have?
2.
2. I got 2 hydrogens. How many do each of those have?
1. No. 8.
So I have a total of 4 valence electrons, right? Again, put the beryllium in the center, hydrogen, hydrogen, oops. I have no electrons left, but I know this compound exists. Sorry, I'm going in and trying to get somebody else in here. I have, how can this be? I have a compound and I have an atom that doesn't have enough electrons around it. Guys, you got to live with it. Sometimes the best you can do is giving it your best shot. And if nothing else works from there, then that is what it is. Sometimes you don't have enough electrons to cover. You don't have enough electrons to cover what you need to. And if that's the occasion, then yes, you can have a compound with less than 8 octet or 8 valence electrons. Are we good with that?
Does that do anything to the element once you combine them?
Does it do any? I'm not understanding, Dylan.
Like, are there any special characteristics because it lacks the 8 valence electrons?
Not that I'm aware of, Dylan.
Okay.
Any questions about this? So A compound can disobey the octet rule because of the fact it just doesn't have enough electrons. Okay? We have another molecule here. Neutral molecule, NO2. N has how many? N
Five.
has how
Five.
many? Thank you. Plus,
16.
not 16.
12.
Not, well, 12 from oxygen. How many total do I have?
Yeah, 12, 12, 12.
How many total valence electrons do I have?
17.
17. Least electronegative goes in the center. An oxygen on one side, an oxygen on the other. Now, Dylan, where do the electrons go on from here?
Around
Joseph? Where do I put the electrons now?
the terminal element.
1, 2, 3, 4, 5, 6. I got 1 electron left. Remember, extra electrons go around the center. Man, let's undo that. Undo that. Thank you. This is why I don't like dots. Okay, so my little electron's going to go around my nitrogen. All right. Still, nitrogen with only 5 around it's not very good. So I'm going to do the best I can. I'm going to take this lone pair and put that down there, making a double bond there. So I have N, O, double bond, O. I can't do anything about it. This is another situation I can't do anything about. This is all I have. This particular compound is something known as a radical. A radical is a molecule with an unpaired electron. It doesn't want to stay in that state. It wants to get out of it. So because it has this radical here, it wants to go and get another electron somehow. So it undergoes further reactions that will try and eliminate that unpaired electron. But this is another way that the octet rule gets disobeyed. Are we good? We understanding this? We good?
I'm good.
Questions? Okay. Now we have a third different way. Believe it or not, the noble gases will react to make some compounds. Xenon can react with fluorine to make xenon tetrafluoride. Blake, how many valence electrons does xenon have?
Is it 6?
Nope. Where's it at in the periodic table?
All the way to the right.
And so how many valence electrons does it have?
0?
No.
8. Sorry, 8. I knew that.
All right, Blake, we'll give you the easy one now. How many does fluorine have?
Fluorine has 4.
No.
-1.
1.
No.
-1.
I have 7.
Thank you. So each fluorine has 7. There are 4 of them. So I have 28 from fluorine. I have a total of 36. Okay. Now, again, Least electronegative in the center. I'm going to put my 4 fluorines out here. I'll make that a little better of an F. It's nice having new toys, you know that? All right, so I have 1, 2, 3, 4. How many did I use up?
8.
So that gives me not 9, 8. That leaves me with how many left?
28. No, 26. 28. Yeah.
Let's try the other math. 28. Okay. Now, Blake, where am I going to put the the next electrons?
Around the fluorine.
1,
So you,
2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have how many electrons left over?
4.
Where do they go?
Xenon.
My rule says they go onto the center atom. But how many electrons does that give xenon?
12.
Is that possible?
No.
Yes, it is.
Ah,
Yes, it is.
tricked me.
As I often do. Okay, I'm going to stop share here. And what I'm going to do is I'm going to go back to the PowerPoint. And we're going to go all the way down. Hopefully I'll be able to find my periodic chart. How can that happen? All right, let's think about this through quantum mechanics. Do you remember when we were talking about the n equal 2? If n equal 2, my L values can be 1 and 0. So I can have p orbitals and I can have s orbitals. I cannot have any d orbitals. Is that not true? Come on, affirm that I'm good. Come on.
Yes.
Yes.
Thank you so much. When n is 2, I cannot have any d orbitals. However, when n is 3, when I have an n of 3, my L values can be 2, 1, or 0. In other words, I have a d, a p, or an s that can go into the third shell. So even though these d electrons fill after the f, they are still in the d orbital. So if I absolutely have to shove some electrons onto xenon, then I am going to be able to use those d orbitals. Anything below the third period, anything below this row I'm showing you right now, can have more than 8 electrons on them because they can employ the d shell. Does that make sense, guys?
Yeah.
Mhm.
All right, and it has to be that way because there are certain compounds which exist. Okay. I'm gonna slip down here. Okay, I'm going to go back to the fewer than 8 electrons. Would you agree that this is a perfectly good Lewis dot structure for BF3? Try it yourself. Fluorine has 7 electrons. Boron has, I got to sit here and think, boron has 3. Yeah, boron has 3 valence electrons. So if I have 3 times 7, that's 21, plus boron's 3, that's 24. I use up 3 going boom, boom, boom. I have 6 from 24. I have 18 left. 2, 4, 6. 8, 10, 12, 14, 16, 18. But if I do that, boron doesn't have enough, correct, guys? Boron only has 3 different bonds to it, has no lone pairs. So what you tend to do is you tend to take the lone pair off one of the fluorines, shove it in between the boron and the fluorine, and you're happy, right?
Yep.
Except for one little thing. What's more electronegative, fluorine or boron?
Boron.
Dylan, look at your periodic table. What's the most electronegative element on the planet?
Fluorine, sorry.
So if fluorine is the most electronegative element on the planet, is it ever going to let boron steal an electron from it?
No.
So having boron have a -1 charge while a fluorine has a +1 charge is absurd. It doesn't exist like that. What really exists is, and I'm going to stop share, go back to the board. Clear this crap. Clear all drawings. What really exists is as boron, fluorine, fluorine, fluorine. Boom, boom, boom. Boom, 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 boom. That is how it exists. Boron does not have 8 electrons. If we go and we study a crystal of boron trifluoride, we will find that the bond angles are exactly 120 degrees. Each one of these bond angles, even though I haven't drawn them that way, each one of them is 120 degrees. If I draw this, because double bonds, undo, because double bonds take up more space than, take up more electronic space than single bonds do. When we get to Vesper, we're going to find this is true. What happens is this pushes down more than this pushes back up. Same thing here, because it has more electron density. Does that make sense? Because it has a double bond. There's more electron density. It pushes these down so that literally the bond angle between those 2 fluorines is less than 120. This is greater than. I did that wrong, didn't I? Sorry. This bond angle is greater than, is this greater? Why am I having a moment here? Is this the less than sign or the greater than sign?
Less than.
Then let's do it the greater than sign. So this bond angle is greater than 120. No, it's, Jesus, Greg. I'm sorry, I'm having a moment today. This one, because we're pushing it down, is less than 120. These 2 are greater than 120. Does that make sense, too? So literally, we can verify that the entire structure is this as opposed to this because of the bond angles. Again, does that make sense, too?
Yeah.
Yes.
All right, we're going very, very good here, guys. And I think I want to stop here. I want to go back to the PowerPoint. All right. There's a compound, PCl5. It exists. Now, Cl has 7 valence electrons. How many things can Cl bond to? It
One.
only has 1 unpaired electron. It can only bond to one thing. So if I have PCl5, that must mean all 5 of those chlorines must be surrounding the phosphorus. So again, phosphorus is in the 3rd shell, so it can incorporate 3d electrons to add that other orbital to accommodate more than 8 electrons. Sulfur hexafluoride, same thing. Now, sometimes we got to look at structures, and we have to realize that we can do it a little better way. I can draw a phosphate ion. By the way, guys, if you are drawing an ion, draw the Lewis structure within brackets, put the charge outside of those brackets. That is the proper way to draw an ion in Lewis dot structures. I can draw phosphorus, a phosphate, just simply this way. Phosphorus, 4 oxygens. Each one of those oxygens has 3 lone pairs. And that's a perfectly good Lewis dot structure. However, if I incorporate the d orbitals and allow one of these oxygens, if I allow one of those oxygens to be a double bond, this gives me, again, 5 orbitals around the p, but look what it does for the charges. I've taken away one of the oxygen charges, and I've taken away the phosphorus charge. Molecules and ions are more stable if they are closer to having 0 charge, if the atoms within the molecule have closer to 0 charge. We're going to learn about that in a second or two when we do formal charges. So if I'm looking at these two, which one of these two has less atoms with a charge on it? Left or right?
The
The
right.
right?
So the right has less charges, therefore it's the better molecule. It's the better way to draw PO4. Notice though, if I take another lone pair and put that in there, although the oxygen becomes 0, the phosphorus at that point will become a -1. And phosphorus is never going to pull an electron away from oxygen. So this is as far as we can go with that. Are we making sense here, guys?
Yeah.
Nothing is earth-shattering or nothing you're about to jump off the Skyway Bridge about, right?
No.
Okay, Blake, I want you to do BI3. Dylan? ICL4 -1. Joe, KRF2. Min, I want you to do ClO3. Or no, ClO2, Min. ClO2 -1. I want you to give this a try, guys. And if I find a pen, I'll give it a try too. Ooh, whoever I gave ClO2 from, they got a break. Okay, I'm done. All four guys. Anybody done?
I'm done.
Who's it, Blake?
Yeah.
Which one do you have, Blake?
I have A, BI3.
Oh, you got the easy one.
Yeah. So I got iodine at 7. And
Okay.
there's 3 of them. And then I got boron at 3. So you add those up and I got 24.
Okay.
And so 24 would be distributed between, so 3 to boron, and then the remaining would go around the iodine, and I didn't have any left over. So,
So it's the same thing as BF3.
yep.
You don't put the double bond in there because iodine is much more likely to have that charge than boron. Good.
Cool.
All right. Who's got, what was the next one? ICl4 -1.
Yep, that's me.
Don't know how many, what do we got?
So I have the I as my central atom with my CLs as terminal. So there's 4 different CLs. Around each CL, I have 3 electron pairs. And then around my ion or my iodine, I have 2 electron pairs.
Lone pairs around iodine. Good.
I couldn't hear you. I'm sorry.
I'm sorry. You got
I
it right,
couldn't-
Dylan.
Okay. All right. Thank you.
I was just praising you for getting it right. I'll stop doing that in the future. Who has KrF2?
Me.
Okay, what do we got?
Well, I had a total of 22 electrons in total, so I had the 2 pairs. In Kr and F. Okay, well, let me just say it like this: F has all 8 valence electrons, with 2 of them connecting to Kr, and then F. Okay,
Other F.
so F has A2 connecting
Okay.
2, and then Kr just has 6 plus the 4, so it has 10.
Exactly. There are 3 lone pairs around Kr, and the Kr is bonded to both Fs, which gives it 12 around, or sorry, excuse me, 10 around it. And Min, ClO2 -1. Min? Min? Okay. Cl has 7. 2 oxygens have 12. 7 and 12 are 19, plus the 1 extra one gives me 20. I put the oxygens on either side, fill them out. That means I had 20 minus the 2 bonds, 16 left. I've got, of those 16 left, 6 go on each of the oxygens for a total of 12. I have 4 left. The chlorine has 2 lone pairs around it. We feel fairly good about this, guys. You feel fairly confident about it? If
Yep.
you're not comfortable, believe me, the Organic Tutor and the Khan Academy, I forget which one I used in the online outline, but it doesn't matter. They're both excellent. Avail yourself of them if you're getting confused about doing Lewis dots, because if you can't do Lewis dots, you are not going to be able to do Vesper. All right. So there are different ways we can draw some of these structures. So if I have carbon dioxide, I can draw them as having 2 double bonds off of the carbon, or having 3 with one of the carbons and a single bond with the other. Is that true, guys?
Yeah.
Okay. Gonna go back to the whiteboard. Okay, let's just see. Remember what I said about atoms and charges, molecules and charges on atoms. The molecule which has the fewest charges on its atoms is going to be the stabler one. Okay, those are my two choices because literally speaking, guys, this is the same one. The charges are going to be the same for this one, whether it's on the left or the right side. Okay. Now, there are two rules we have to deal with. One is we have to figure out what the charge of the atom is within the molecule. And the more charges on the atoms within the molecule, the less stabler it is. The other thing we have to deal with is that if we have a negative charge, that negative charge has to go on the more electronegative element. Again, I'm going to repeat that. The more charges on the atoms within the molecule make it less stabler. The other rule we have to adhere to is if we have a negative charge, the negative charge is going to go around the atom with that is more electronegative. So how do I figure out these charges? I do it using something called formal charge. And the formal charge is equal to the normal valence electrons. That is, if I'm just looking up the compound and the atom in the periodic chart, this is how many valence electrons are around that atom as I'm looking at it in the periodic chart. From this, I am subtracting the lone pair electrons. You notice I'm not saying lone pairs. I'm saying lone pair electrons. To that, I'm going to add the bonding electrons divided by 2. So why am I dividing the bonding electrons by 2? That's because they're sharing. Like if I have these three bonds here, one of those electrons came from oxygen, one came from the carbon. They're sharing them all. So they only get them half the time. So if they're only getting them half the time, then because of that, I'm dividing the bonding electrons by 2. Let's look at this oxygen. We're going to deal with left. Okay, if I'm dealing with this oxygen, how many normal valence electrons does it have? How many valence electrons does oxygen have, guys?
8.
No?
No.
6.
Thank you. So I'm going to put this in for that number. Now, around that oxygen, how many lone pair electrons do I have?
2.
No, I have 2
Four,
lone
four.
pairs. Each pair contains 2 electrons. So how many lone pair electrons do I have?
4.
4. Now, how many bonding electrons do I have?
2.
No, I have two bonding
Oh,
pairs.
no, it's 4, yeah, but then you divide by 2.
So I have 6 minus 4 plus 4 over 2. My formal charge on that is 0, correct?
Correct.
Can you see that this one's the same thing as that one? Will you allow me to just put a 0 there without proving it?
No.
No, you're not going to allow me?
Yeah, I was kidding.
All right, now let's consider the carbon. How many normal valence electrons does carbon have?
4.
4. So my formal charge is going to be equal to 4. How many lone pairs are around that carbon?
0.
How many bonding?
8 divided by 2, so 4.
So what is the formal charge on that carbon?
0.
0. All right, now let's deal with this aminal. Okay, I have this oxygen. Again, we're dealing with the triple bonded. I hate Etch-a-Sketch. I always hated it as a kid. My triple bond oxygen. What is the number of valence electrons around a normal oxygen? Come on, guys.
6.
6 minus. How many lone pair electrons does that have?
1.
1 pair. How many electrons?
Oh, 2.
2.
Yeah.
How many bonding electrons does it have?
3.
3 bonding
6.
pairs. 6.
6.
Got to be careful when we're dealing with pairs versus electrons. So 6 minus 2 plus 6 over 2. This has a plus
Negative
1
1.
charge.
Oh, yeah.
My carbon. How many lone pairs are around my carbon?
2.
How many lone pairs are around my carbon?
2. Yeah.
None.
Oh.
There
What
are
about
no lone pairs. There are 8
bonds?
bonding electrons,
Gotcha.
no lone pairs. So it has 0 lone pair electrons. And as I just said, it has 8 over 2. So the charge on my carbon is 0. Let's work the other oxygen. How many valence electrons?
6.
How many lone pair electrons?
2. Lone pair. 3.
How many? Remember, 6. Remember, guys, we're talking lone pair electrons. Each line equals 2.
2. Yeah. Yeah.
Think lone
So
pair as no bonding, non-bonding.
lone pair means non-bonding. So
Gotcha.
how many bonding electrons do I have?
So that'd be 2.
So now my formal charge is 6 minus 6 plus 2 over 2. Its
-1.
formal charge is -1. Now, looking at these two, which one has the least amount of formal charge? And guys,
Either this-
when I'm asking that question, I'm not asking you to add up all the formal charges, because the formal charges will all add up to be the same. Trust me on this. What I'm asking you when I say which molecule has less formal charge, I'm asking you which atoms within the molecule have less formal charge, left or right.
Less formal, I would go with the right.
This
the
one
left
has, this
looks-
oxygen has a +1. This has a -1. Are those charges? This one's 0, 0, and 0.
Yeah, but less formal, I thought it was like a bad thing. So I thought we want to go for the more formal one. So I could see, okay.
No, you want the less charges within the molecule. So this is a better choice. Carbon dioxide is a linear molecule, and I'll get into that at some later time. It can be proven to be a linear molecule. I guess this is a linear molecule too, but the bond lengths change in this, so it gets a little funky. Are we good, guys?
Yeah.
All right. Do I need to keep this up here any longer?
No. Mm-mm.
Okay, now I am going to blow your minds. How many different formulas do you think you can make from this? You are not restricted by putting carbon in the center. Can I put the carbon in the center? Can I do that? Can I do that?
Yes.
Just for kicks and giggles, can I leave the nitrogen in the center?
Yes.
Undo. Okay. Or could I put the sulfur in the center? Can I do that?
Yes.
All right. Nitrogen has 5, sulfur 6 for 11. Carbon has another 4 for 15. That extra minus up there means 16 electrons. So literally speaking, this can be drawn the same way as CO2. Remember the different ways we said to draw CO2. We could have double bonds here, right? Or we can involve triple bonds. And can you see that the one I just drew is different than the one I'm going to be drawing? Okay. Are those the 3 I can draw from the carbon being in the center? Is that true? Is it true, gentlemen?
Yeah.
Thank you. I was beginning to believe you all went out to eat dinner already. Okay, same thing here. I can put 2 double bonds between them. Double bond or the lone pairs out there. I can put a C triple bond N or I could put the triple bond on the other side. Anybody want to guess what the 3 different formulas for the last one is? No guesses? No guesses at all. You guys have no intrigue, do you? No intrigue at all. Or you're just bored to death at this point. What is it, guys? Bored to death?
I'm here. I just did this earlier, so I'm being quiet.
Yes, I know you had, Ian. You've already listened to this once. Can anybody think of any other combinations? God, I hope not. All right, let's start on the right here. If I'm dealing with carbon, how many valence electrons? Guys, do this once and we won't have to deal with it anymore. How many valence electrons on carbon?
6 or 4.
4. How many lone pair electrons?
4,
Bonding electrons?
2. 4
2
divided by 2.
pairs.
I just do the math.
So if I have this, what is my formal charge on this carbon?
-2.
-2. Can you see that this carbon's the same as this one?
Correct.
So it also is a -2. All right. Sulfur. How many valence electrons around sulfur?
6.
Lone pairs
0.
and bonding.
8 divided by 2. 4.
So what is the formal charge on my sulfur?
2.
My nitrogen, how many lone pairs?
4
Bonding,
plus 4 divided by 2.
2. 5 minus 4 plus 2,
-1.
minus 1. Okay, God, this is gonna last forever. Okay, let's see what we can figure out. This nitrogen has a -1 on it, right? It's the same as that environment, so I'm gonna call that -1. Okay, we good there?
Yes.
All right, guys, all the sulfurs are going to be the same because all these sulfurs have no lone pairs and 8 bonding electrons. So each one of those is going to be a +2. Make sense?
Correct.
Okay, let's deal with this carbon. This carbon is 4 minus how many lone pairs?
2
How many bonding?
plus 6 divided by 2.
So what's the charge on that carbon?
-1.
This nitrogen, 5 minus
6.
plus
2 divided by 2. 1.
So what's the charge on that nitrogen?
-2.
Okay, let's see what we can do. We got a triple bonded carbon here. We got one right there, so that one's a -1. Okay, we got a single bonded nitrogen, which is the same as this over here. So that's going to be a -2. All right. This carbon. How many lone pair electrons? Lone pair electrons, guys.
6.
Bonding.
2 divided by 2. -3.
-3. This nitrogen, I got 5 minus 2 plus 6
Negative
over 2. It's a 0. Okay. Now, this carbon's the same as this one. Do you understand why I'm saying they're the same? It's the orientation. Stop doing that. The orientation is the same here, okay? Do you understand that, guys?
Yep.
This carbon has 3 lone pairs and 1 bonding, same as this. So the formal charges are going to be the same. Okay, I got a triple bonded nitrogen with 1 lone pair. This one's also going to have 0. All right, nitrogen. All 3 nitrogens are going to be the same. And they're
-1.
going to be 5 minus 0 plus 8 over 2. These are all going to be +1. Sulfur. Top one. Tell me what it is. 4 lone pairs plus 4 bonding. It's 0. Are you guys just bored in general, or are you just waiting for me to finally mercifully end this?
I think I understand it.
I'm good.
Okay. -1. And this one is 6 minus 2 plus 6/2 for a plus 1. All right. I'm just doing this because I know what they are, right? Okay, they're all there. Yes, lots of work. Absolute lots of work to do this problem. I did this in a way to do 2 different things. Okay, now can you pick out 2 compounds that have the least amount of formal charge to them?
The top left and the second left.
So we're talking about these 2, correct?
Yep.
Do you all see that? Do you all see that, guys? Everyone else has a whole lot more formal charge. This only has 1 negative charge to it, right?
Yeah.
Yes.
All right, now we have to choose between these 2. And that's going to be the determining force. In the top one, the negative charge is held by the nitrogen. In the bottom one, the negative charge is held by the sulfur. Which one is more electronegative, nitrogen or sulfur?
Sulfur?
What's your second guess?
Nitrogen.
Guys, the more fluorine is the most electronegative. So the closer you get to fluorine, the more electronegative it is. And yes, I know nitrogen and sulfur are a little bit off, but nitrogen, if you look it up in a chart, is more electronegative than sulfur. Which one is the better formula?
The top one?
The top one. Okay. I went through all that to illustrate a couple things, one of which is how to do formal charges. You guys are following along pretty well on that. Okay. The second thing is I wanted you to be able to see that the more favored compound, more favored Lewis structure is the one which has the negative charge on the more electronegative element. Last thing, do you remember I said one of my first rules is to put the more electronegative element in the center? I'm sorry, the least electronegative element in the center. Do you remember my putting that in as one of my rules?
Yes.
Somebody answer yes. Okay, look at this. All of these nitrogens all have a +1 charge. All the sulfurs have a +2 charge. But when I put my least electronegative in there, they all have a 0 charge. This is why you want to put your least electronegative in the center. Questions about this, guys? By the way, how irritating is my drawing on here? Nobody's
fine.
saying anything, so it must be very annoying.
Nah, it's really good.
Okay. We're going to get a little further than the morning class did. Okay? And that we are going to talk about something called resonance. First of all, throw it in your notes right now. Resonance involves manipulation of double and triple bonds. If the double and triple bond can be moved to an equal place in the molecule, then you have something called resonance. I'm going to get into this more when I'm talking about molecular orbital theory and hybridization. But what actually happens in this molecule is this has a free pi orbital. This has a free pi orbital. This has a free pi orbital. What happens is those electrons get dispersed through all of these pi orbitals. So in effect, the double bond is not really on the right oxygen. It could just as easily be on the left one. And there is an equal sharing of electrons. What happens in resonance is it makes the overall molecule more stable. Okay, so I'm looking at this Lewis dot structure. Is there any special reason I put the double bond on the right oxygen? Any special reason I did that? Could it just as easily be on the left side?
Yeah.
So if that's the case, if I can interchange those two structures, if I can draw a good Lewis structure in which I have manipulated the double bond, that means the molecule has resonance, it's more stable, and because it's more stable, it can hold together itself better. So, the actual proof of this, when you have a double bond, the bond length is shortened. So if there was really if the double bond stayed with one oxygen as opposed to the other, you would have one bond length shorter than the other. But we find that the bond lengths are equal. You might think of resonance as something like mixing paint. Just like green is a synthesis of blue and yellow, when we're dealing with ozone, it's a synthesis of these two structures so that literally you get that electron density that's distributed throughout the entire molecule. Again, you can only have resonance, A, if you have double and triple bonds, B, if you can manipulate them. I have this molecule, which is actually an organic acid. It's formic acid. Okay. Is there anything that says that the double bond has to be on the horizontal oxygen as opposed to the vertical? Is there anything that says that? Is there any special stabilization that occurs with the double bond being in the horizontal position or the vertical position? They're both the same. They're literally both the same. So because they're both the same, the electrons are said to be delocalized. They're spread over this entire area of the molecule. Again, I have SO2. SO2 has one double bond, one single bond. They exist in resonance. Can that have resonance?
No, because if you just swap the oxygens, it's still the same formula.
I can't manipulate the double bonds there. I cannot manipulate those double bonds to make resonance. Unless I do something else, and that is make a triple bond and a single bond. It does have a little bit of resonance, but this structure is so much stronger than the other one that there's no real resonance there. Looks like I'm going to be able to get it all done tonight. Okay, I also have to talk about polar covalent bonds. And I'm bored at this point. You guys bored? I'm going to show you a video. I'm going to stop the share here a second. Hopefully I can find the video. And hopefully I can pull it up here. Uh-huh. Nope, it's not there. The atom, okay. Yeah, okay. Believe me, once you see this video, you'll understand polar bonds more than anything I can say to you. Okay. Bear with me a second. Crap. Somehow I have to stop share. Trying to get it. Yes. Are you seeing the black screen here, guys?
Yeah.
Yes.
You hearing the music?
Welcome to Dogs Teaching Chemistry.
Are you
Our
hearing
first
it?
lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom. Thanks for watching, and we'll see you guys next time.
Okay, do we now understand polar bonds?
Yes.
Okay, if you get two elements together with one of them, if they're not exactly the same, one's going to pull on the electrons a little more than the other. And if we have fluorine hooked with hydrogen, what's going to happen is they're sharing the electrons, but the electron spends more time on the fluorine than the hydrogen. So literally speaking, what happens is the fluorine end has a slightly negative charge and the hydrogen end has a slightly positive charge. Again, electronegativity. It is a very, very important issue here. So if I have a pure covalent bond, basically the electrons are shared, but they are shared equally. If I have a polar covalent bond, that means one of them has more electronegativity than the other, a significant amount. If that's the case, then the electron is going to spend more time around one of the atoms than the other, and the atom that spends more time around is going to have a slight negative charge. The one that has less time around it is going to be a slight positive charge. And the last is the electronegativities get to be so large that the one atom steals the electron completely from the other. In ionic bonds, we're talking about metals and nonmetals. If you want to look at it, if you're a numbers type of guy, if you're between 0 and 0.5 difference in electronegativity, you have nonpolar bonding. If you have between 0.5 and 2, you have polar bonding. If the electronegativity differences are greater than 2, you are going to have ionic bonds. Generally speaking, when you are talking about a polar bond, you either put this that's a delta sign right there. You either put a delta negative and delta positive on the molecule, or you draw an arrow. The direction of the head of the arrow is where the negative charge is going. And that's a useless slide. And I'm not going to get into this. We're going to get into enthalpy of reactions next time, guys. And conveniently enough, I'm at the end of my time. Anybody have any questions about what we discussed? We went through disobeying the octet rule and Lewis dots. We went through formal charges, trying to decide which the best molecules were. And we went through polarity and resonance. Any questions on any of those topics, ladies and gentlemen? No ladies are here tonight.
Nope.
If anybody can tell me how these other people are getting through this, please let me know. I enjoy being humbled. And that happens every test because some of these people are amazing in which they're learning this stuff on their own. Okay, guys. Y'all take care. I will see you again on Thursday then, unless you're coming in a couple minutes.
Adios.
Thank
See
you.
ya.
I will see you again at 7:30 then.
Did we not move the the lab to Thursday?
Did we?
I don't know. I feel like is today. Hold on.
Today's Tuesday. It's always been on Tuesday, Dylan. I don't
Well,
recall
I'm
sending
talking
any.
Veterans Day.
I'm sorry, Dylan.
I was talking Veterans Day, but that's tomorrow. Yeah.
Yeah, I had to. I'm actually teaching class tomorrow, not at SPC. I've got a lab lecture that I've had scheduled on Wednesdays, so I'm just going to hold it. Whoever shows. If nobody shows, then I'll at least have the meeting recorded that they can do that.
Yeah, I have my biology lecture and lab tomorrow, and I got the two confused with. Sorry
Did I
about
send it out? I didn't send it out to you guys, did I?
No, I thought we had discussed it. We
Oh.
had discussed it in my biology lab, not
Okay.
yours. Got the two mixed up.
Okay, good enough. Good enough. Hey, Dylan, you did a hell of a job on that last test.
Thank you.
If I didn't compliment you before, I wanted to make sure I did. Okay,
Thank you very much.
keep it up.
I'll
Keep it
see
up.
you in about 15 minutes or 45 minutes.
45 minutes.